Hello everyone, and thank you for joining us.
The conference is now starting. All attendees can now hear you.
Hello everyone, and thank you for joining us for this webinar with GigaSpaces, Amazon, and Bazoo Media. We'll be talking about how to build scalable applications on the Amazon Elastic Compute Cloud. And let's get started. We'll start with some housekeeping items. I hope everybody can see the slide and can hear the audio. First item of housekeeping that I wanted to bring up is that for those of you who may have a problem hearing the audio through the call number or don't have a local call number or any of those issues, we are broadcasting the audio via the web. To listen to this broadcast, you can simply go to ubroadcast.com and enter the station ID that's on the screen now, 14945, and click on Jump to Show, and you'll be able to hear the audio via the web. Second housekeeping item that I wanted to bring up before we begin is that everybody, except for the speakers, all of the attendees today are silenced. They cannot speak. However, you are most welcome to submit your question, and we will leave time for Q&A at the end. And you can do that via text through the GoToWebinar interface that hopefully you can figure out how to do that. And we will respond to some of the questions in writing during the session, and some of them we will answer at the end Q&A session. Last housekeeping item is that we are recording this web session, and it will be available on the GigaSpaces website. You can find this and other relevant links on gigaspaces.com/EC2, and we will make this recording available. So allow me to introduce the distinguished group of speakers we have today. I myself am Geva Perry, Chief Marketing Officer at GigaSpaces, and we're going to kick off today's session with Jeff Barr from Amazon Web Services. Jeff is traveling the world, speaking about Amazon services and cloud computing in general, blogging about it, writing about it, and some of you may have met or seen him. We'll also be joined by Ilya Sturin, who's the chief architect at Bazoo Media. Bazoo Media is a startup company that is using the GigaSpaces solution on the Amazon cloud. And Ilya is going to present to us, tell us a little bit about his company and how they are leveraging the GigaSpaces solution on EC2. I think that'll be very interesting. And finally, Owen Taylor from GigaSpaces. Owen is another global speaker, speaking at many conferences, blogging, writing. Some of you may have heard or seen him. And Owen will actually be showing us a live demo running on EC2, showing the GigaSpaces solution. We're going to see some cool stuff. The demo is usually quite an exciting piece there. So, without further ado, I'm going to hand it off to Jeff Barr from Amazon. And Jeff will be telling us a little bit about the Elastic Compute Cloud and Amazon Web Services in general. So, Jeff, please go ahead.
Okay, well, hello everybody, and thank you for coming. I'd like to start off by giving an introduction to the Amazon Web Services and to our Elastic Compute Cloud to really warm you up for the main event, which is for you to be able to hear about the GigaSpaces product. So for the last couple of years at Amazon, we've been investing heavily in a concept that we call web scale computing. The idea with web scale computing is you can use our multi-billion-dollar investment in technology to scale up and scale down your application on demand. And instead of the old model of resourcing your system where you had to design your hardware layout in advance and procure exactly how much hardware that you needed, with web scale computing, you use exactly what you need when you need it. You then go ahead and you pay for exactly what you use. You don't have any upfront costs. There's no charge to join the program. You don't pay for any services at all until you actually use them. So you can literally put together a very, very large-scale plan for infrastructure with no capital investment whatsoever. When you start to use storage or servers or messaging or bandwidth, you're billed based on actual usage for what you actually use. You're billed monthly on your credit card through your Amazon Web Services developer account. Because of this, we really take away a lot of the challenges that used to be a real issue when you started to think about putting together a large-scale web application. As a developer, as an entrepreneur, you really get to focus on your idea. Instead of worrying about acquiring and scaling data centers, thinking about buying hardware, thinking about negotiating leases and dealing with contracts and dealing with power and cooling and bandwidth, you simply leave all the heavy lifting to Amazon. And we're very happy to do that on behalf of our community. We have a developer community which is now in excess of 370,000 developers, representing large organizations, medium-sized organizations, schools, scientists, researchers, individuals, hobbyists, startups, entrepreneurs. Pretty much every type of developer you can imagine is part of our community. Let's move on to the next slide now. Okay, on the next slide. Okay, so this is a catalog of some of our more popular infrastructure class web services. The first service is called EC2, the Elastic Compute Cloud. The idea here is you can rent servers from us, virtual servers from us by the hour, to get compute capacity on an as-needed basis. Working closely with EC2 is another service called the Simple Storage Service, or S3. This is scalable, redundant object storage in the cloud. You store objects in the cloud that can be anywhere between 1 byte up to 5 gigabytes at a time. They're copied redundantly to multiple locations and then made available. If you choose to mark them for public access, they can be then used for web object storage, web pages, and media files and so forth, or you can keep them private, use them for backup or any individual application storage that you'd like. Amazon DevPay is a billing and account management service. You use DevPay to actually wrap the other services, and you as an entrepreneur can create your own business model and billing plan around the other services, and then expose that billing plan to your customers. And then Amazon take care of actually measuring how much of the services your customers are using. Your customers go through an Amazon sign-up page, sign up for the services you offer, and we take care of all the difficulties of tracking and measuring and billing your customers. So once again, you get to focus on your application. The Simple Queue service, or SQS, is a messaging tool. Offers reliable and scalable hosted messaging in the cloud. You can create within the scope of your Amazon developer account any number of these message queues. You can load them up with any number of messages that you need to as you use the messages to buffer communication between the different parts of your scalable web services application. Amazon SimpleDB is a scalable, redundant database in the cloud for storage and retrieval of structured data. And then the flexible payment service is a developer-focused payment service. And using the FPS APIs, you can actually programmatically move money between any two entities, be those humans or computers or bank accounts. Let's move to the next slide, please.
There's a slight lag there, but
all right, let's take a little closer look at the Elastic Compute Cloud. As I said before, the idea with the Elastic Compute Cloud is you get web service access to computing power on demand. So what that means is you actually can make web service calls into the Amazon cloud, and those calls can do things such as give you a list of the available spaces where you can launch your servers, give you a list of what are called AMIs, Amazon Machine Images you can launch. You can then do the actual launch request yourself to the cloud, where you make a request to the cloud. You reference a machine image, which is a pre-configured disk. You specify how many instances that you would like to launch, 1, 10, 50, 100, thousands if you'd like. You launch these instances through the cloud. We find available machines. We put your machine image on them, boot them up, assign them IP addresses, DNS names, and then through the cloud APIs, you can control and manage these dynamic server instances. You pay for them by the hour. You can keep them running for just an hour if that's all you need. If you need to keep them running for days or months, you can do that as well. There's actually 5 different instance sizes where each instance is a different amount of CPU power and virtual cores and RAM and disk storage that range in price from 10 to 80 cents per hour. With any of these instance sizes, you launch them and you pay for exactly how many clock hours that you use of these instances. There's a lot of flexibility inherent in the compute cloud. You have these varied instance sizes as I just described. You have a full network security model. So with that, you can control on a very fine-grained, very, very detailed basis exactly which of your instances are allowed to talk to each other and which ones are allowed to communicate with the outside world. Only the communication that you enable is allowed. We have elastic IP addresses, so you can actually get IP addresses and then map those to your servers. If you need to have long-term permanent IP addresses that might actually need to be mapped from server to server during the course of your operation, you would do that. And then multiple availability zones, so you can actually choose to launch different servers in different Amazon locations and data centers. We support a number of different Linux distributions, and we also support Open Solaris. We support Fedora, the Red Hat Enterprise Linux, Ubuntu, and many, many other Linux distributions. At the core of EC2 is something really important called an AMI, an Amazon Machine Image. The AMI is a pre-configured disk with your operating system, your services, and your applications loaded on there, configured, and ready to boot up. We have a large catalog of pre-built AMIs, but you as a developer can also build your own AMI and customize it with exactly what you would like to have start up when you launch your machine instances. And also, as you'll learn just a little bit later, GigaSpaces has built their own AMI with their server built onto that AMI, and you'll learn soon how that actually works in conjunction with EC2 and the cloud. Let's go to the next slide, please. Okay, this is a management tool called ElasticFox. And this is a very straightforward Firefox extension that allows you to, in the top left panel, you get to see a list of all the different AMIs, Amazon Machine Images, that are available to boot. In the bottom, you get to actually see the set of AMIs or instances that are running in the scope of your account. There's a set of menus and tabs and context menus that give you very complete and direct control of what is running inside your cloud. So that's what I have to say today to get you started, and I'll look forward to communicating with you more through our Q&A session.
Thanks so much, Jeff. We will actually revisit the Firefox plugin that you just showed, ElasticFox, in the demo. We'll use it for the actual demo to deploy Amazon Machine Images and so on. So we'll take a closer look at that a little later. Okay, next I'm up. And I wanted to tell also, because we have a pretty diverse and large audience, some of you may be familiar with GigaSpaces, some of you may not. Just a brief introduction to the company. GigaSpaces is a software company that's been around for since 2000. We have essentially built an elastic application server or scale-out application server that's optimized for distributed and virtualized environments. And in many ways, we've been deployed, as you can see some of our customers here, in very large organizations for a variety of applications that are typically mission-critical, often transactional, data-intensive, real-time-ish, and event-driven applications that are by nature difficult to scale out or horizontally scale across many machines, such as in a cloud environment. And that's a challenge we've been addressing within organizations. In many ways, we have been born for the cloud, and the cloud was born for us, and we'll show you some of how that works and what are some of the benefits. So the main challenge, or sort of the economic opportunity that we're trying to address with our cloud solution, is the fact that there's a very big gap between organizations' peak and average loads. Here you can see a couple of examples. And these gaps could be because of constant transaction, data, and user growth. It could also be because of seasonal things, and we can see here the Amazon.com example, how near the holiday season, there's always a surge in application load, or in this case, website page views, as an indicator for that. It could also be because of unexpected and unanticipated events that happen that cause these peaks. And the result of that is that organizations have to over-provision their IT resources, both hardware and software. Over-provision meaning they have to anticipate what would be the peak capacity that they want to handle, and they need to provision those resources to be able to handle that peak and then some. However, on average, the loads are much lower. So we end up with an industry statistic of about 15 to 20% utilization rates of data centers. This obviously is cause for a lot of waste because our resources are idle 80 to 85% of the time. This trend is somewhat changing with the introduction of virtualization technology, and so on, because it's become a competitive necessity for organizations to achieve much higher utilization, reduce those IT costs. I actually just saw yesterday a survey that, once again in 2009, as we're looking at, a tough economy, the top priority for CIOs is server consolidation and reduction and so on. And we can see, that this could be one of the areas where they're trying to focus on how do we achieve better utilization of these resources. The problem, by the way, the opposite problem, if you don't provision enough, you might face a scalability disaster. In other words, if you don't have the resources required to handle your application load when it peaks, you might face a much more terrible prospect, which is the application crashes, needless to say, lost direct revenues, customer frustration, brand damage, customer defections, and so on. And here on the screen, we have a number of stories where we've seen these types of disasters happen recently. So, in this respect, cloud computing, I think this is one of the key value props of cloud computing, is that you can provision these resources on demand when you need them, so you always have the necessary resources at your fingertips to handle those peak loads. And as Jeff already said, you only pay for them when you actually use them, and then you release those resources, and you don't have to pay for them anymore. Of course, the other benefit is that you're essentially outsourcing the management of your data center and your infrastructure. However, there's a gap. Applications, the way they've been architected, or are still being architected in many cases, they can't just scale on demand. They can't just grow from 4 servers to 20 servers to 200 servers when we want them to, and then shrink back again. They're not architected that way. They're architected in a much more rigid way, and we'll describe why that happens. So one is they can't scale on demand. The other problem is they don't scale linearly. What does that mean? There's actually some diminishing returns. So if my first server can process 1,000 transactions per second, my second server will only be able to process 600 transactions per second, third server 400 transactions, and so on and so on. So the more transactions or other data processing that I need to perform, the more I need to perform, the more expensive it becomes per process, per transaction. The other thing is, at some point, the application simply won't be able to scale anymore. And I just noticed a typo on this slide. I apologize. It should be the scalability wall. So at some point, the application can't scale anymore theoretically. And this will be caused because of contention in the application. For example, waiting on a central database, waiting on a central messaging system that persists to disk, waiting on a distributed transaction manager, or other elements in our application that essentially halt the transaction process, and it can't continue until they are done, and that creates contention, which creates our bottleneck. Here you can see some of the economic effect of that as the graph describes, and we took here a server, and this is not just the hardware cost, of course, 20 grand. That would be an extremely high-end server, but it's fully loaded with middleware, operating system, and so on. Let's say it costs us about 20 grand per server, and as you can see, because of these diminishing returns, the more throughput we need to handle, the cost grows exponentially. So what do we want to achieve? We want to achieve linear scalability on demand, meaning I essentially stick another server, or in the case of the cloud, and specifically Amazon EC2, I simply provision another server, request another Amazon instance, machine image instance from Amazon, and scale linearly. So if one server or one AMI in the case of EC2 can process 1,000 transactions, 2 can process 2,000, and so on, there are no diminishing returns, and I can scale on demand. And by the way, I want to be able to do that without changing the application code. So that's a big, that's really sort of the holy grail here, in essence, because we can always write everything in software. It's all ones and zeros. The trick is how do you do it with no work. And then, from an economic perspective, our graph will look more like the red line, which scales linearly and does not hit that wall. So just to understand why is it difficult, the way applications are architected today or traditionally, to scale on demand and to scale linearly. Essentially, it's because the application is built in tiers that are silos. So each one of these tiers, and a typical example would be the messaging tier, the data tier, services, or the business logic tier. There could be other tiers such as the presentation tier, web tier, and so on. Each one of them usually runs it's a different product. It runs on physically separate servers. So each one is a silo in essence. In order for a transaction to complete, it has to jump across these different components over the network and be serialized, deserialized, and so on, creating latency and creating some of those bottlenecks that we spoke about. In addition, things like the database become a central point where things have to wait on it, and creating exactly that contention that I was describing before. In addition, all of this is extremely complex, so if I just want to scale, I need to scale each of the tiers and then integrate so that they scale together. So you can see why it becomes quite difficult to scale on demand. So my application actually looks something like this, and here you see again those tiers that I described before. And each one of them has to have its own high availability, its own scalability model. So we can see it's an extremely complex many-to-many relationship problem here. And this slide is intentionally very loaded and noisy because that's the reality of the architecture of many applications. So we'll try to look at an alternative approach, a solution to this problem. And we'll present GigaSpace's Elastic Application Server, or Scale-Out Application Server. So the approach goes like this, and for this, the purpose of the explanation, I'm using a sample application, a simple order management application that, in order to complete the transaction, I need to perform 3 services. I need to validate the order, in other words, check if the customer is in good standing, that the order was properly submitted, and so on. Then check inventory to see if that whatever is being purchased, the widget, is available, and essentially execute the order, meaning sending it to the warehouse, shipping, billing, and so on. So in a typical, first thing that we do is we actually co-locate the services. All the 3 services that are simply Java or .NET or C++ objects will be running within the same process. Next thing we'll do, we'll co-locate the data and we'll put it in memory local to that process, embedded in that process as well. Third thing, we'll do the same thing with the messaging. Messaging will also be handled local and in memory. And we'll wrap this whole thing in a container that can be managed. And we'll call this container a processing unit. Ilya will actually, I think, mention this a little later. So now, in order to complete a transaction, it happens fully in process, in memory, obviously in a single box, and can be managed as one. And what does it mean managed as one? For example, if I want to scale this application, because now my application volumes are growing, as I just said, I simply provision additional servers, and I create more instances of that processing unit that is fully contains my entire application, as I said. And now the transaction can be processed in parallel across these many servers. And because there's no interaction among these different servers, so I'm not going over the network and doing other unnatural acts that I need to do in a traditional distributed system, I can essentially scale linearly, because if one server can process 1,000 transactions per second, when I add a second one, there's no reason it too won't be able to process 1,000 transactions, and so on. Now, from a development and management perspective, this entire thing, this cluster, is really handled as one. There's no, all of the handling of this highly distributed, parallelizable environment is done through mere configuration. There's no code changes. The developer and the runtime environment doesn't have to sort of be aware of this complexity, if you will. Now, another question that often comes up is, if we're doing everything in memory, what about the database? The database now moves away from the critical path of the transaction and essentially moves to be a background. Data is persisted to the database asynchronously, or after the fact, after the transaction is committed. And that's, of course, for auditing purposes, archiving, reporting, and so on for future use. But I've moved the database from being a bottleneck in the critical path of the transaction. Finally, there's the question of resiliency or fault tolerance. With this model, again, because we're using an in-memory data model, every primary processing unit will have a backup, a hot, active backup that receives the data with synchronous replication, typically, although that's not necessary depending on the application requirements. And when the primary fails, or should the primary fail, the backup, the system actually will fail over to the backup, which now becomes the primary. And the system also has a self-healing capability. So it will now create another instance that will be the new backup for our new primary. And so I have complete failover without losing a single transaction. It's instantaneous almost. And I always maintain that resilience no matter what happens. Finally, I want to say a word about the programming model. GigaSpaces supports and lets you actually bring on your existing applications to the cloud through this model. Here are some of the programming models that we support today, and we're continuously adding more. Our approach is we want to be the best runtime environment, the most scalable, highly performing, reliable runtime environment. We're not getting into programming language religious wars. So, of course, we support Java, some of the enterprise Java APIs such as JMS and JDBC, or you can write your applications in POJOs using a Spring framework. You can write .NET, C++, dynamic languages is support we've added in our just released 6.5 version. And specifically, we're talking about JVM-based dynamic languages such as JavaScript, Groovy, JRuby. And other common sort of development framework or platforms such as the Mule open source enterprise service bus. All of that is done through our own open source API, which we call OpenSpaces, and you can check it out at openspaces.org. So finally, I just want to talk about some of the things you can do with on the cloud. So number one, of course, for startups such as Bazoo Media, who Ilya is going to tell us a little bit about very shortly, they can simply scale their business on demand when they need it without making large upfront investments in hardware and software. So it obviously makes it easier to start a business, to start a company. And for larger organizations, we're seeing quite a few interesting uses of the cloud, except simply running apps on the cloud and being able to scale on demand to handle peak loads. Some large organizations are already using it for testing and development cycles. And if you think about that, that in many cases is sort of a classic use case because it could be extremely time-consuming and difficult to provision resources for short terms within a large organization. And therefore, testing and development cycles tend to lengthen out just because of this reason. So it's a very cool use case for them. Many of our enterprise customers are also interested just in the idea that they're essentially future-proofing their application, that if and when they would want to get on the cloud, by building it with a GigaSpaces solution, they can do that at any time down the road without any code changes. Another interesting notion is the idea of the hybrid cloud, meaning you might have on-premise resources to handle that average load I was speaking about, and when you need to handle those peak loads, the system will dynamically grow to provision resources from the cloud to handle those peaks. I think that's really an exciting use case. Could be the killer app for cloud computing. Finally, GigaSpaces, through the AMIs that we developed, as Jeff has mentioned, we are solving what we're seeing that many customers that came to EC2, in other words, they didn't come from the GigaSpaces direction. They came from trying to run their apps on EC2, and particularly those apps that I mentioned, those apps that tend to be transactional, data-intensive, real-time-ish, event-driven apps, and they're facing all sorts of specific technical challenges, which I listed here, such as issues of data access and the latency that causes and how to persist on the cloud, such as issues of fault tolerance and reliability. What do I do if my AMI fails? Well, the answer in GigaSpace is you don't care, because as I've just shown, it will fail over and self-heal. Obviously, quicker development cycles, because really it is already an application platform, an application server built for a cloud environment. And finally, obviously that we can truly scale our applications on demand and linearly on the cloud. With that, I'm going to pass it over to Ilya Stern, who's going to tell us now about how his company, Bazoo Media, is using the GigaSpaces solution on EC2. Ilya, please.
Yep. Thanks. Hello, my name is Ilya Stern, and I'm the Chief Architect at Bazoo Media. This slide just provides kind of a brief overview of our organization. So let's just jump right into it. We're an initial stage startup. We're currently financed by the founders and the initial small revenue stream that we have. We provide real-time tracking, messaging, scoring for global athletic events. We also provide athletic event data management, live online results and tracking. Our events range in scalability and basically size requirements. And currently we're focused on North American race and marathon and triathlon markets. And we're later going to probably capture other athletic event markets. We have a pretty variable and unpredictable peak and off-peak times during those events. We also have downtime between events. Race events are usually clustered during the weekend. So, for example, Monday through Thursday is our current downtime for our messaging application. We can go to the next slide. So what were the requirements for us building the messaging backend? Let's take a look at them. We needed near real-time mobile messaging. We have to provide pretty close to real-time messaging for people to be interested in our service. Of course, just like any other application, we don't want any single point of failure. We need to horizontally scale to handle races with variable messaging needs and peak times. We also wanted a flexible deployment model. Although we have some formula figuring out when a peak time occurs in our application, we also could get a bunch of feeds of events which would require messaging backend to scale at any given point in time and day. So we needed to basically have a flexible deployment model that will allow us to scale on demand. We also needed monitoring functionality to monitor the health of our system as well as the event itself. Races are very intense for administrators, not just for athletes. So many things can go wrong at the race, and we needed a way basically to know these issues as soon as they happen. So we have a monitoring functionality that gathers various data points from a running system in GigaSpaces and from a space, and we apply various business rules to this data in order to determine what actions we can take. We can go to the next slide. So what were some of the issues that we needed to be addressed to accomplish our requirements? Being a small company, we didn't have much in forms of capital to acquire expensive systems. even the capital that we had, we probably had other better things to spend our money on wisely. So basically, we needed no upfront capital to acquire expensive hardware. We also realized pretty early that relational databases are a bottleneck. There's some issues that with relational databases and scalability. If you want to have an active-active, for example, configuration when more than one database node is responsible for processing your data, in most cases you have to replicate this data synchronously, and synchronous replications are basically distributed transactions, which we'll discuss in a bit. Also, clustered database products that usually require static infrastructure and don't work very well in clouds. This is very true of most database replication technologies. Even if you're willing to take a scalability hit, basically, you're now stuck with rather static database cluster infrastructure. To achieve acceptable levels of scalability, you basically need a huge financial investment by expensive high-performance hardware, network infrastructure, Oracle RACs, various clustered file system products, and so on. The other thing that we realized, and I think everybody who's done any distributed applications have realized that as well, that traditional distributed transactions do not scale. XA algorithms and their likes are very, very inefficient, and they affect performance exponentially every time you add another node to participate in that transaction. So in order to resolve these issues, we basically needed a way to distribute and partition our data, distribute our processing, and reduce latency by storing data in some sort of a memory where we wouldn't have to go through a network in order to access that data. So we can go to the next slide.
You're on it.
So some of the... Sorry. Were you...
My fault. Just letting you know I've moved the slide forward.
Okay, yeah. Some of the solutions that we basically thought about as we needed to resolve the issues I just described. Basically, many applications that require database scalability have to partition their data in the database to distribute their load of data and distribute their processing of that data in that particular database. Usually, this is very application-based and based on application semantics. So usually, it's your responsibility to know how you want to logically and physically separate this data. This is usually a pretty challenging thing due to the fact that the data in a relational database is stored in such a way that to allow efficient access and to relational joins. So once you start separating this data, you're faced with many issues that are described. So the other thing is don't use distributed transactions. There are cases where you are going to need to use distributed transactions, but in most cases you can accomplish most of your tasks without it. If you need data consistency across distributed data, you can use eventual consistency or compensating transactions to accomplish this. There are not many applications that truly require distributed transactions. So many of the people that are using it could probably take a good look at their actual application semantics and figure out that they can bypass distributed transactions. Also, Amazon, Google, and the likes were resolving these particular issues that I just described with relational databases in their own way. And they basically build more powerful database models like SimpleDB, Bigtable, HBase, Hypertable, and so on. The last two are based on actually the Bigtable Google implementation. They build them in order to be able to scale their database operations, and these are basically distributed database models that are not relational. There's a huge learning curve associated with learning these models and implementing them. There's also the JavaSpaces tuple space architecture that allows you to store data in an efficient distributed storage model. And JavaSpaces is basically a standard, and there are various implementations. GigaSpaces is probably the first and the most powerful implementation of it. And GigaSpaces offers declarative configuration support for scaling your architecture. We needed also to bring the data as close to the place where it's going to be queried, processed, and to store it in memory. By doing that, we basically get rid of the network latency, and that allows us immediate access to any data that we need on the partition where we're actually processing this data. And one thing that I wanted to point out is if space-based architectures, you can implement space-based architectures with GigaSpaces, and it is a very simple architecture. So when you first read about it, you think, wow, it's too simple to be, too good to be true. But it is very scalable and very powerful. So let's go to the next slide. This is a pretty high-level overview of some of the components involved in our application. The gray box represents external systems that basically read RFID chips of athletes that complete various events in the race. This info is then relayed through a web service, through a REST web service, to the EC2 system. We do use a relational database. I mean, there's still needs for relational databases in many cases, especially for when you want to do reporting or some kind of historical persisting of data. So we do use a relational database for that. You can see that in our static box. The EC2 system is comprised of various processing units. Those are basically services that are programmed and implemented completely separate from each other, and then we deploy them in the EC2 GigaSpaces container. One of the services is the web service endpoints that's responsible for reading all of the events. Then we have the event worker, the SMS worker, which is basically the messaging, message processing. And then we have the DB workers. And all of these work sort of asynchronously from each other, and they interact by passing messages to each other through the through the space architecture. So the event worker, for example, validates the event that comes in, and then it creates various tasks for the message worker and the database worker to complete, and those complete asynchronously. We also have a monitoring processing unit that's constantly collecting data from the space and writing that data to the database for our administrative panel. And we use this administrative panel to basically look at any of the issues that are going on at the race at any particular point in time, and then we apply a rules engine and business rules to those events to figure out what compensating actions do we want to take against those faults. We can go to the next slide, please. So GigaSpaces on EC2. As we know, we can, of course, run GigaSpaces on non-cloud environments, and before EC2 and before cloud environments were created, that's exactly how most people were running GigaSpaces. What does it do for us? It allows us to scale our services in a flexible and cost-effective way. Allows for on-demand runtime scaling up and down, which is very important for us to be able to scale down, because when we no longer utilize certain resources, we want to ensure that we can, reduce our costs by pulling those resources down. We don't have a lot of capital, as I mentioned, so we only pay for processing hours as we consume during the races when we're actually charging for our services. We also don't have to worry about installing or testing GigaSpaces on supported servers. This is done for us by having pre-configured EC2 AMIs tested by GigaSpace engineers. So all we have to basically do is just start, configure, and save the AMI, customize it in any way you want, and then export an AMI and then use it later. And that's a pretty small process, and it doesn't require a lot of expertise in figuring out whether GigaSpaces will work on various systems or not. We also, get self-healing and failover, as was mentioned earlier by GigaSpaces. So we're given self-healing failover functionality pretty much out of the box, and GigaSpaces has declarative configuration for that particular functionality. And the last slide is just some architectural comments on GigaSpaces. We currently decided not to use a pure space-based architecture model. This was an original decision when we were first starting out. Basically, the way we steered away from the model was that we didn't collocate our data with the services, and it was because our application semantics at the time didn't allow us to partition the data all to a to a particular partition. So we originally decided against the SBA model, but through some empirical evidence, we decided that we should probably go to an SBA model for ease of deployment and configuration. We decided to scale each service individually and not collocate together. For us, this provided, at the time, more flexibility and scalability, but at the expense of a little bit more maintenance. So basically, now we're looking to go to a pure SBA model. Our system works as is in the model, the non-SBA model, but the great thing about GigaSpaces is that going to an SBA model is done all declaratively through configuration. We do not have to touch any of the application code. All of the processing units and services that are already written, we're just able to package them and collocate them with a space all in one particular processing unit and achieve the service-based architecture purity. That pretty much completes my slides, so I'll pass this back on to GigaSpaces.
Excellent. Thank you so much, Ilya. That was great, great presentation, and thanks for sharing with everybody. Before I turn it to Owen Taylor for a demo, and we are slightly behind schedule, but in any case, if we've been receiving some questions through the Q&A throughout the presentations, please, this is pretty much your last opportunity to send in your questions, and hopefully we'll have some time for Q&A. We'll probably stay about 10 minutes later than the original schedule. For those of you who can hang around to listen to the Q&A, that'd be great. And with that, I'll hand it to Owen for the exciting live demo on EC2. Owen?
Hey there. Thank you, Geva. I'm here with Geva in New York. Those of you on the radio may notice that you can still hear me. And I am about to demonstrate something live, which is always a fun thing to do with software. I'm sure the other developers and architects who've had to do that for their bosses and for their potential customers understand exactly how happy I am right now and excited. In any case, what we're going to do is demonstrate the order processing application that Geva referred to earlier, where there's several different services that build a workflow. The order arrives from an external client as a new entity into the system. So in comes this feed of orders. Once they arrive, they're interesting to one service and one service only because of their state. So it's basically content-based routing in a sense. But it's routing in reverse because the services will pluck them out of the space where they reside, these orders, in order to process them. So the accounting service is going to take the new orders. And when it's done checking to make sure that the person or the order is approvable because it has the right credit authorization, etc., it will write them back as approved. Once they're approved, then logistics, the next service in the chain, will pick up the approved orders and check inventory to see if there's enough widgets in stock for that particular SKU on that order. If there are, then the order gets shipped. If not, it gets written back as unshippable because there's not enough stock. What happens next is the broken order cleaner is going to look for things that are unshippable, and it's going to restock the items. So this is actually based on a real-world application, but we're condensing the timeline here so that we can automate the restocking in just a few hundred milliseconds rather than doing it over months as it might take for larger widgets. Our widgets are highly portable, and we can restock them on demand. What it does show is sort of the cooperation between services that's easily attained when you have a space as the centerpiece of your architecture. And we call this a space-based architecture. In addition, the space-based architecture can be collapsed so that these services that might initially be designed as remote from one another, highly decoupled and really independent in every way, you can achieve tremendously low latency by collapsing the architecture and running those services in the same runtime as the space. And what it does is avoids many, many remote calls. And you avoid the marshalling costs, you avoid the risk of going across the network and the possible failures that might ensue as a result. So you get a much more predictable application once you discover that you can run your services in the same runtime as this host space where the information and events are passing through. All right, so let me go ahead and show you this stuff running. I've got a small deployment of this I believe, out on the Amazon EC2, and then I'll scale it by deploying it on a bigger set of servers out on the EC2, and I'll show you how to do that, which is kind of fun. So let me go out here. Right now I've got a few images. This is the ElasticFox interface, which is free and a lot of fun to use. There are hundreds and hundreds of Amazon images. This little filter box is a blessing for me. It allows me to select only the AMIs that are of particular interest to a particular project. So here I've got my GigaSpaces 6.5_C for cluster as my filter, and that allows me to just see these 3 AMIs. If I didn't have that, I'd be seeing a whole bunch of information that might be good for browsing, but not so good for getting my work done quickly, and certainly not demoing as I hope to right now. So I'm going to go back and put this filter in, and now I can see just those 3 AMIs that are relevant to this clustering demonstration that I'm going to show you. So we prepared 3 separate disk images, or AMIs, one of which is the host for the bootstrap of our system, which is the lookup service and the management service. Another AMI is the image for the user interface that will allow us to watch the behavior of our application as made evident through the state of the objects that are being executed and worked on within the space. And indeed see statistics and other things, and I'll show you that in a minute. And then the third one there is the cluster node itself, and that's where the work gets done. That's where the processing units actually execute their labors. Down in the bottom of this, these are the sort of definitions up in this area here. Down in the lower pane are my instances, and these are the ones that I've started already in anticipation of doing this demonstration. I've got one management node, I've got one user interface node, and I've got 2 cluster nodes where I'm going to be running processing units. Now let me switch to the VMC that's looking at the user interface out there in the cloud, and I am not able to find it. Something has changed on my system while the PowerPoint went on. So we'll try and connect again, I guess. Yep, Putty saw a network failure during the presentation to this point. So let's see if I can connect again. Let me refresh this and see if we're still connected to these things out there. My apologies. This is why it's called a live demo. Looks like somehow my network was disconnected. So I'm going to reconnect and see if we can't find these images again. We're hoping for the best here. My apologies. This is the real world, and we're doing a real demo out there with a network, and my network card somehow got disabled during this presentation. I don't know how that happened, but I've got 2 running. That's the reason, probably. Someone may have bumped it or something. Anyway, I'm now looking and seeing I've got a connection. I don't know if I'll be able to connect with the correct one. We'll keep trying. I'm looking for the AMI that matches the user interface, which is ending in the letter A. And that's this one here. So I'm going to right-click on that. And it looks like my browser's not happy either because I lost my connection. So the live demo portion may suffer some latency here as I get restarted. Perhaps, Geva, you could use your laptop to look over the questions, and while I get this all set back up again, you could answer some of the questions that may have been posted. This may take me a few minutes to sort of reconnect and reestablish my interface here with my frozen browser. My browser's not responding, so it lost the connection and decided to die. So, Geva, I'm going to let you talk while I work here.
Okay, so let's jump to the Q&A session.
And don't watch the screen while I get this all running again.
All right, first question was that there was a question about the GigaSpaces approach to scalability. The asker was impressed with the simplicity and so on. There was a question, is there any requirement from the cloud or clouds of different flavors to do anything unique or special? The answer to that is no. The GigaSpaces product itself, by the way, is written in Java. So essentially, any environment, any OS, hardware, and so on that has a JVM, it can run on. As I said, though, from a programming model perspective, we also support .NET and C++, so it can also run those types of applications. But the GigaSpace product itself is Java-based, so it can be portable, etc. And the container, that processing unit, that container really is what allows you to move things quite easily, as I said, between on-premise to the cloud, among clouds, and so on. So hopefully that addresses that question. The other question that we had is, because the data, the transactional data or the system of record is now in memory, the question is, what if my data is too large to fit in one node? So if you were following my presentation, I am essentially creating multiple nodes. So transactions or data are processed in parallel on multiple nodes, and I'm essentially partitioning the data across multiple nodes so that if I have a need for increased data capacity, I can simply add nodes and they will contain subsets of the data and be partitioned. The interesting thing, though, is then I also, GigaSpaces transparently makes sure that the correct message or transaction that needs to be processed goes to the correct node that holds the relevant data. So again, that complexity is shielded from the developer by the GigaSpaces system. Another question, Ilya, this is for you. The asker is asking if this type of solution implies that you need to write your application from scratch. So I'm wondering, what was your experience with that, and how would you respond to that?
Well, yeah. I mean, in our use case, we did write it from scratch. I mean, we're a new company, and to use the idea of using space-based architectures and GigaSpaces specifically was done right away. As far as if you have a pre-existing application and how easy it would be to port it to the solution, I think it depends on your application. If your application was written in a loosely coupled way where every single component has some kind of a interface and you can easily separate that into its own component, I would think it will be pretty easy to transfer that application to this sort of a what you can call a service-based architecture, right? So as long as you have clear separation between services of your application and clear loose coupling there, I would think it would be pretty straightforward to support this application.
Yeah, and I would add, I had mentioned during my presentation the different programming models that we support. So again, if your existing application is written using Spring, it'll be pretty much seamless. The J2E APIs that we support, such as JMS, JDBC, it will be pretty seamless. .NET as well, C++. So, and as Ilya mentioned, it really depends. But we're seeing actually quite a few customers who, whether it's on the cloud or not, are moving to our architecture with very little or zero code changes in many cases. And like I said, we're actually continuously adding more and more such frameworks and models that we support. For example, in our recently released 6.5, as I mentioned, we added dynamic languages and we added seamless support for Mule ESB. So if you have an existing application using Mule, it will be completely transparent, no code changes, to benefit from the scalability, performance, and reliability of GigaSpaces for your Mule application.
Yeah, one more thing I wanted to mention is the deployment units, the PUs for GigaSpaces, are basically a reflection of the OSGI standard. So, and I don't know how many people have heard of OSGI, but it's basically an older standard, but it's now coming to light in the industry of packaging and distributing various components within a framework. So as long as, and I think moving your application to OSGI-based distribution model will be a benefit to the application, whether you were to use GigaSpaces or not. And the other benefit would be that you can just deploy these components in the GigaSpaces environment.
Yeah, we've just joined, by the way, the OSGI Alliance. We're going to be quite active there and introduce more and more support for it in our upcoming releases. I'll answer one more question, then we'll go back to Owen. We seem to have resolved our internal office network problems that we had here. The final question, and then we'll go back to Q&A after Owen is done with the demo, was, can you load balance between the primary and the backup? The asker is asking, isn't it wasteful to have idle backups? The answer is yes. You can load balance, and the way it's actually done, I didn't go into that level of detail in my presentation, but the way you would actually, our customers do this in practice.
The demo will demonstrate it actually.
Okay, so is that each node has a primary on it and a backup for another primary. So essentially, on each node, I'll have, on one node, for example, I'll have primary A and backup B, and the other node, primary B and backup A, and that's the way it's handled. So essentially, all the servers are processing at any given moment. And of course, if there's a failure, meaning now I'm going to have A and B on the same machine, processing for a little bit until I can recover and launch that additional new backup, then for a while there'll be a strain on the system, and once I've launched that additional node, it'll spread out again and resume smooth operations, and Owen will show that in the demo. So with that, and once again, we'll go back to Q&A, so if you have more questions, please do send them along. And with that, though, I'll pass it on to Owen, back to Owen for the demo.
Okay, so probably, even though I told you not to watch, you may have noticed that I was using the Firefox ElasticFox plugin there to actually, I terminated the existing user interface instance and started a new one. That was just easier for me to clean it up. I left the grid running. I left the actual management instance and the other processing unit ready instances running, and all I had to do was reload the user interface and get my VNC connection up and running again from my laptop. So nothing out on Amazon had any conflicts. It was just my laptop through our network here in New York reaching out to it. So here we are connected again, and what I'm going to do right now is you may notice at the bottom of this pane that's at the front of the screen here, it looks a little small on my desktop, but hopefully you can see it. There's this little pane of information. You see what looks like computers. There's 4 of them across the bottom. Each one has an IP address. Those are actually Amazon IP addresses. So those are each running hosts or containers that are ready to host your application services. And I've actually got 2 physical Amazon machine images. And again, the word physical is kind of elusive here or meaningless because we're out in the cloud. So the truth is Amazon may have decided to make my 2 physical images somehow manifested in a way I can't even imagine. But in any case, somewhere on the cloud I've got these 2 distinct machine images running. And within those machine images, I've got 2 containers, which are the software hosting environments that GigaSpaces provides. They're called grid service containers. And so I've got 4 of those guys running, 2 on each of those images. 2 images, 4 containers. That's why you see 4 logical machines, because each container to us is representative of a runtime environment that you can now leverage. So in this way, if you have a very powerful machine, you can run many of these containers on one machine. Some of our customers run us on the mainframe. You can also use commodity hardware and have just 1 or 2, as I'm doing in this demonstration, running on each machine. So I click this little button up here, and at the top left corner of the user interface, and this brings up the deployment wizard. And there you can see I've got this full-blown order system that I've been talking about. I'm going to deploy into this set of 4 possible logical deployment containers 2 partitions. So I'm going to take my existing order processing application, which has those 3 services I described, and the space, and I'm going to break it up into 2 partitions. And I'm doing that not with code. I'm doing that with configuration here at runtime or at deploy time while I decide what is the topology that I would like to use. And these things can be determined as part of an XML descriptor, which is part of our OSGI-friendly bundling. I'm clicking deploy, and now my 2 partitions, each with a backup, are going to be assigned to the 4 available logical runtime containers. So what I have here is 2 partitions, each with a backup, and that makes 4 different instances that are going to represent functionality within my application that's going to process orders. Each one of those instances has a complete complement of services. Each one of them has the accounting service, has the logistics service, and has the order cleaning service. And each one also contains a space. The difference between the primary and the backup is that the backup won't be active until its primary fails, if it ever does. And as you can see, we've now deployed 4 green happy deployments. You can see the IP addresses here, showing that the primary for number 1 partition is running on 208, and the backup is running on 112. Very different network addresses here, showing that if the primary were to fail, we won't lose our backup. And that's good news, of course. Let's go ahead and execute the feed, which will write several orders into the system. And while it's doing that, we can take a look and watch the space respond. So over here, I have a command line client that I'm going to kick off within this Unix shell, and it's going to feed orders into the system, and we'll watch it process. So what it's doing is it's looking up the bootstrap. It's going out and getting the cluster proxy, and the client doesn't know if there's 1 instance or 1,000 instances within that clustered configuration, or even if it's clustered at all. All the client knows is that there's a named resource available that's going to process orders. So the client here is the feed that's going to write 2,000 orders, which it's finished doing, and now it's monitoring and watching as the orders get shipped, which is the final processing stage. And as you can see, that it's plugging away there. I'm going to go back to my Amazon utility here, the ElasticFox, and I'm going to create some more nodes so I can run this faster, because we all want to go faster. So let's launch some new instances of this AMI, which is the container environment that I mentioned I can use. And let's add 8 more of them, which will give me a total of 10. And on each one of these, I will again run 2 logical containers. So I've got 8 more machine images, 16 more runtime environments that can host services and spaces for me. So I'm making that request within the ElasticFox as a background task, just to prepare for my scaling exercise that I want to show you guys. In the meantime, of course, we're busy processing orders, and you can see the object count is changing here. If we go into the Operations tab here in the space view of the user interface, we can see details regarding the types of information that is within the space that these services are addressing. So we've got orders, for instance, and if we look at the order objects, we can query them while they're being processed. And this creates a very powerful development and runtime environment where you can see the state of the information and the messages you're passing around as it's being passed around between various different services. This creates a great monitoring solution, as well as a great programmatic solution for achieving all kinds of different problem resolutions. How about that? You can also watch the transactions fly through the air, which is always fun, proving that we're actually mutating information here as we process the orders. And sometimes you'll see several objects being locked. We have 2 partitions that are active, but each partition has 3 or more active services, 4 active services. Therefore, there are many transactions executing. And we can also watch statistics fly through the air. Here's what's going on within my cluster. And you can see that we've done quite a few writes, 4,000, and we've done quite a few updates of information, more than almost 7,000 there. And takes are topping 8,000. Takes are when we do the final stage of removing things, mutating it before we then go ahead and update it. So it looks like we may be getting close to the conclusion of our processing, which is good news. Let's go to our command line shell and see what it tells us. Yes, it took 130 seconds to process 2,000 orders, and we restocked 218 items because they were low on stock and they couldn't be processed the first time round. They had to be resubmitted. This is just proving that we're actually mutating information and dealing with some failure conditions and recovering from them. Now what we're going to do is take advantage of those extra servers that we've asked for. Let's go make sure that we have some servers here that we've launched. You see they're all saying pending in this view. I'm going to now click on the refresh button and see how many of them are actually active. And look at that. Amazon was very helpful in making sure that all the ones I asked for became available. So now I can go ahead and very quickly take my application to new levels of scalability. You remember, perhaps you can help me remember, it took 130 seconds to process 2,000 orders. We're going to re-execute the same set of informational tasks there in just a second. Let's go ahead and use this extra room we've just added. If we look in the details, we had 4 grid service containers before. Now we have 20 down here at the bottom of the screen. That's good news for us because we want to go faster and we can now scale linearly, assuming we've used a proper space-based architecture. So let's see what that means to us as a business trying to process orders that may have increased in number or have increased in complexity, causing us to be challenged. So we've gone out and found some more available resources, and we're going to leverage them. So we're going to take our FB order system, and this time, instead of having 2 partitions, we'll have 10. 5 times as many. And we'll still have 1 backup, so we can have a reliable deployment here. Let me just make sure this is actually responding to me. Hope our network stays up for the duration here. I think we're okay. Oh, I know what I need to do. I need to say that it's partitioned. There we go. That was a user interface, user error moment there. And we'll make sure that none of the backups run on the same machine as the primaries. I think that's always a good idea. And then we'll deploy it. So again, I'm not going into the code. I'm not recompiling anything. I'm not changing my deployment unit at all in a physical sense. All I'm doing is within this management utility, specifying that I want a different level of service. I want to go faster. I want to take advantage of more machine images and more containers so that I can process my orders faster. And let's do a little math. 130. Well, you guys are probably smart enough to do this yourself, but I'm going to go ahead and use Python. 130 divided by 5, 26 seconds. So in an ideal world, with pure linear scaling, by adding those additional machine images and hosting a proportionate number of containers within them, and having now 5 times as many, we should be able to execute 2,000 orders in near 26 seconds, or in, well, let's imagine an absolute solution that's purely linear and see how close we can get. There we go. We fully deployed. Successful deployment. Our new, much larger cluster is now running. We have 10 primary servers and 10 backups. Each one has the full complement of services and a space. And here we can see they're all green. Or we will when this refreshes. It says 20 alive. There we go. So we have 20 alive cluster member instances, and that's good news. So let's go ahead and run our client again against our 20 available resources. So there's the same client kicking off. It goes out and finds its cluster proxy. This time the cluster proxy is aware of 20 nodes instead of only 4, and it begins to respond very quickly, as you can see, indicating that work is being done at a much more rapid rate. We are able to execute those 2,000 orders and process them in much less time. And I'm betting, I'm crossing my fingers to get close to 30 seconds here. Oh my goodness, there you go. Okay, so that was a very, very, very effective example. We actually managed, this is good. It took exactly 26 seconds. So life is good. Let's go ahead and show you failover while we're at it. Let's just, since we're having a good day, let's see what we can do. We're going to go back here and we're going to open up a connection to one of these running containers. And this will only take a few more seconds. As you can see, it only takes 26 seconds or so to execute now. So just bear with me for another 30 seconds and I'll just show you how fun this is. PS-A, grep Java. There we go. We got 2 containers running on this machine image, which is what we expected, 2 per machine. So what we're going to do is we're going to do kill all -9 Java, but we are not going to execute that until we start running the actual client again. So let's go back to our client. We're going to re-execute the client again, and when it starts processing, I'm going to kill off 2 of my running nodes and see what happens in terms of failover. And what happens in terms of performance? It'll probably be a bit of a performance impact, but we'll see how much that is. Here we go. It's shipping. So let's kill off 2 containers. We'll re-execute the PS, and you can see there's no Java processes running there. If we go to our VNC client, we can see we only have 18 alive instead of 20 in that view. And 2 of them went gray. You see that? That's not the healthy response we want from a system, right? We want them to be green. We want them to be happy and green. And look, they're happy and green. Wait a minute. I hardly even finished my sentence and they were happy and green. You see, this is called self-healing. And in the background, the orders are all processed. And it took an extra 11 seconds. Ladies and gentlemen, I feel vindicated having recovered from my initial network connection error. This shows you the power of the Amazon platform to provision new hardware on the fly. It shows you the power of the GigaSpaces platform to execute business logic in a reliable and scalable fashion. And I'm done. Thank you so much for your patience and in waiting for me to get this up and running.
Thanks a lot, Owen. That was great. Actually, we are, since we're 15 minutes already going on, I think we'll wrap it up. If anybody has any more questions to us, please feel free to send them to us at ec2@gigaspaces.com via email. Also visit our EC2 page at gigaspaces.com/EC2. You can find some of our per usage pricing information there, white papers, a walkthrough that actually Owen recorded that shows you how to get your app up and running, and some other pieces of information. So thank you everybody for joining again, and we'll see you all soon. Bye-bye.